speaking about R-equivalence on automorphism group of automorphism groups of associative algebras.
Thank you. Thanks to the organizer for giving me the opportunity to talk in this conference. So today I'm going to talk about some geometric property of algebraic groups, and so I'll stick to mostly automorphism groups of associative algebras. And so let's look for today's plan. So first we recall some basic preliminaries about affine algebraic groups, and then we see motivation. I mean, why we need to bother about automorphism groups of algebras, and then some rationality properties which we are going to discuss in this talk, mainly rational, stably rational, and R-equivalence. And R-equivalence is a sort of property that you can think of as like a generalization of path connectedness for topological space. So I discuss those things, and then we'll see some examples how things happens for automorphism groups of finite dimensional associative algebra, and then we see the main theorems and last summary. Okay, so let's move forward. Okay, so throughout my talk, I'll be over arbitrary field, and so any affine algebraic group, we mean just a Zariski closed subgroup of Ln over a field K, and we can also think of them as a functor from the category of K algebras to the category of groups. And I'll be stressing over this connected algebraic groups. That means its underlying variety is reduced. So these are the assumptions. This connected algebraic groups will work over. So now let's see some examples. Okay, so your affine line itself you can think of an algebraic groups, and then affine line minus a point you can think of as an algebraic group, which is denoted by GM, and this is GA. It's a unipotent group, and then we have this PGLN, which is the GLN quotiented by its center. That is also an algebraic group. And we have this, our main object to study, automorphism groups of finite dimensional associative. These are algebraic. And obviously the classical groups, you cannot forget. So these are all groups, but things to note that this may not be connected always. So we'll work with the identity components of this text. So these are the part of affine algebraic groups. Any questions? So I think everyone knows this thing. Now let's move to why we need to bother about automorphism groups of algebra. So thinking algebraic groups, so algebraic group means affine as automorphism groups of algebra. So this study was started in 1960 by Andre Weil. So understanding algebraic groups as automorphism groups of algebra. But he able to achieve for certain classes of adjoint absolutely simple classical type groups A and B and C and D and not D4. As a not trilitarian D4, as the automorphism groups of finite dimensional algebra with involution. Then it was always been asked that whether we can always understand any algebraic groups as automorphism groups of sound. And recently in 2003, this is proved by Gordy and Popov that okay, you take your favorite algebraic groups, then there is always existent finite dimensional simple algebra whose automorphism groups is going to be your algebra. So this is the theorem that, and there is only a little bit of restriction is there on the field that your field has at least 8 elements, and which is true most of the cases. So you can remove some basic cases and then understand your affine algebraic K group. You take your favorite algebraic K group, then there exists a finite dimensional simple algebra A such that your group is of this form, and also there is no restriction of connectedness. So anything you can take. So there is always exists a finite dimensional simple. So this motivates us to study algebraic groups as through automorphism groups of algebra. But the thing is that these algebras are not at all easy to handle. The main problem is that these algebras are not at all easy, and also these are may not be associated. So then the main problem occurs. So this is the motivation why we look to automorphism groups of algebra. Now, okay, so these are the parts of motivation that why we should bother about automorphism groups of. Any questions? No. Now we come to the main topic, the geometric property we are going to discuss today. mainly the rationality and stably rationality. What is it? So we fix any arbitrary field and we call a irreducible variety X to be rational if it is birational to some affine space. And we call it the stably rational if you take a product with affine space that is birational to an affine. So what do you mean by birational? So you take two varieties X and Y over K. So we call X is birational to Y if you can find open set inside X, which is defined over K, and B inside Y, which is also defined over K, such that U is isomorphic to Y. So then we'll call these two varieties are birational to each other. And rational variety means if your variety is birational to some affine space or not. And stably rational means it is a little bit far. Then you take a product with your affine space and whether that is birational to some affine space or not. So these are most, important property for algebraic geometers. To determining whether a variety is rational or not, and that's a very tricky and difficult problem in general for in algebraic geometry. So in this talk, we are going to discuss about the rationality and stable rationality properties of the group, connected algebraic group. And so what does that mean? That a connected algebraic group G over T is rational or stably rational if its underlying variety is rational or stably rational. So basically, we are going to study this problem for algebraic group. And as you can see, the first example, the GLN is always that over anything. So this is thing about rationality and stable rationality. Now we come to the another property that is called R-equivalence. So this is a little bit of similar sort of property like path connectedness in a topological space. So what do you know by path connectedness in a topological space? So 2 points are, so you take X to be any topological space here. Then you said 2 point X and Y belongs to X are path connected if you have a continuous map such that f of 0 is your X and f of Y is your Y. So this sort of property, what about for algebraic variety, you can ask of. So then we come up with a more general notion. So this is valid for any irreducible variety, but I'm talking for connected algebraic groups. So what this R-equivalence says that, so you take let G to be a connected algebraic group over a fit K. Then we define 2 points X and Y to be R-equivalent if there exists a rational map. So what do you mean by a rational map? That means it defines over open set on this affine line, such that you can have a f of 0 is X and f of 1 is Y. So you see that since we are working our setup is changed from the topological space to this algebraic geometry. So we need to replace that closed interval by a affine line because I need to stay in this setup. So and the rational map is a much more general notion than this continuous maps. So then we'll call these 2 points are R-equivalent points in algebraic. So this part is over. Now we'll go to what is now. So now you collect all those points. The set of points is GK, K rational points, which are R-equivalent to a identity. That means you can somehow get a map. You take any points and your identity is there. Now can you give a rational map so that you can connect that point to identity? So you collect all those points where these maps are exist, and this will form a normal subgroup of GK, and we denoted this by RG. Now, how this is related? So, and also, if you think of the equivalence classes in K rational points, that if you define the equivalence relation that okay, X and Y are related if and only if they are R equivalent. Then it will give you a class, R equivalent classes, and you can actually identify that R equivalence class with this group. So this is a group, this is the equivalence class. These are actually isomorphic. I'm not isomorphic, I mean, it sums are equal because this may not have a group structure, but this has a group structure. But it may not be an algebraic group. So there are lots of questions about this group, that GK mod RGK. Now then this comes to the notion called R-triviality. So let G be a connected algebraic group over K, and G is said to be R-trivial for if for every field extension F over K, your G F rational points and you take the R-equivalence class, that is trivial. That means always you have a sort of path between 2 points. This property means that you always sort of path between 2 points. And you can take, for example, your if you take a finite dimensional associative algebra and take the inner automorphism groups, then this group is always R-trivial. For example, if you take your specialize A to be a matrix algebra, M and K, then your A to be M and K, then your automorphism group is actually inner automorphism.
Any condition
And anything.
That's it.
Everything, yeah. So for R-triviality, you need to have true for all field extension. I mean, it can happen that for some extension it is true, but maybe not to some other extent. So then we cannot treat the group to be R-trivial.
Not straight over the
Over algebraic closure. Actually, I'll come to that. So for algebraic groups, everything is over algebraic closure. Everything is true. That is also that. Yeah.
So these you can say this.
Yeah. I mean, you are saying that if X and Y are R-equivalents and Y to Z. Yeah. So you can prove that there is a proof. Yeah, I can. Yeah. So you can directly. So if you have a map from X to Y and Y to Z, you can get directly a path from X to Z. And this is actually PGLA. But for variety, it is not actually exactly true. But if you took for groups, you can do this. You can do some sort of operation. So that's why it will help you. But for variety, you need a bunch of maps from coming from here to here. So you cannot have an equivalence relation. You have a so then you take the equivalence relation generated by the thing. And now come to this example. If you take the matrix algebra, the automorphism groups is PGLM, you know, and that is actually R-trivial. You can prove that. So this is the part of the because this is a matrix algebra. So Skolem method tell you that this group will be PGLA. All inner automorphism, all maps are inner. So then these are the 3 properties which are going to look for our talk. But for the so when you want to study these properties for groups, algebraic groups, I think you need to fix some group and over some field. Otherwise, it must be a more difficult problem because if you try to prove things for general things, then it will be difficult. So here in this talk, we are fixing our group to be automorphism groups of finite dimensional series. Now, what you are asking actually, this is true over algebraically closed field. That you take this proof very long ago in 1950 that you take a connected affine algebraic group over an algebraically closed field, then G is always rational. So over algebraically closed field, your all groups are connected algebraic groups are always rational. And we have a this implication that rational implies stably rational implies R-trivial. And this is true over any field. This is not required algebraically closed. But the theorem is true for algebraically closed field that you take any connected affine algebraic group, then over algebraically closed field always rational. So that means it's always stably rational, it's always R-trivial.
You see why how I get stably rational to R-trivial with that.
I mean, yeah, no, but I mean, so basically you're having that. So this R-trivial is birational infinity. If you have 2 variety X and Y, which are birational to each other, then their R-equivalence class is the same. So you can use directly that and get your answer for stably rational. So over algebraic closed field, this problem doesn't make any sense now because this is already proved that over algebraic closed field, the groups are always rational. What about arbitrary field? So you need to ask this question over. Yeah. Okay. So now we'll move forward to our question. So let's look at this group. This is an important group. So you take A to be a central simple associative algebra. That means your center is the field A, and you have an involution. Involution means is a map which satisfies this property. Sigma x plus y is sigma x plus sigma y, and it is anti-linear, not anti-linear, anti-multiplication. That means sigma AB equal to sigma B, sigma A, and sigma squared is identity. And you consider this group automorph aught A comma sigma, which is actually all automorphism you're taking, so that it sort of commute with this thing. So this certainly is a smaller group than automorphism groups of algebra. And R-triviality properties has been lots of studied for this group by many authors, by many mathematicians, like for example, Marcury, Philip Chill, Porimala, all this have done lots of work for this type of groups, because this will give you all sort of classical groups, A and B and C and D and other than the trilitarian type. So this has already studied by lots of mathematics. Now suppose you remove all such conditions. So you remove central, simple, you don't have sigma. So then you just only have this automorphism of finite dimensional associative. You remove all such conditions. There is nothing now. Now what about those cases? What could be the answer? Whether these groups are always R-trivial, whether these groups are always rational over any field. So these are the questions I am dealing with. And for non, and just to I want to make a remark that for non-associative case, things are very hard. Like if you take just a non-associative algebra, finite dimensional, and trying to prove whether that group is R-trivial or rational, that's a very hard. I mean, there are lots of open questions there. Recently, there are some progresses saying for F4 groups, which we all know that occurs as an automorphism of Jordan, exceptional Albert algebras. So now we'll see the case of automorphism of finite dimensional associative. Okay, so start with examples. That will be the best we can always do. First, when you want to do some problem, you start with examples. So you take your algebra. So we fix the notation GA. That is denotes the identity component of the automorphism group, because I'll show you that this group is not going to be always connected. So we just stick to the identity component of this group, and then you take the all matrix algebra, just direct semi-simple algebra over to field K. Then you use the Skolem method and find that the group is just a direct sum of PGLN, and which is and your triviality properties will nicely for product of varieties or product of groups. So that's why this group is R-trivial. And if you remember the implication chain, that rational implies stably rational, stably implies R-trivial. So R-triviality is a necessary condition for a group to be checking whether it is rational or not. So before going to a rationality, if you can somehow, okay, I have a group whose R-trivial group is not trivial, then you can no need to check whether it is rational or not. So that's why R-triviality is an important property to check for groups. Then you fix a finite dimensional vector space V and take the exterior algebra. What is that? You just take you have V, then you consider the tensor algebra and quotiented by the ideal. So this is your algebra A. So this is give you a finite dimensional algebra, and which is non-commutative but associative. And if you calculate, you can calculate that group, automorphism group. It comes out to be GLN semi-direct product with unipotent group. And I just want to mention that unipotent groups are always rational. So this implies that this group is also rational and hence R-trivial. These are the positive examples giving you that okay, maybe you can think okay, always is going to be R-trivial or not. something like that. Then we come to the commutative case. So you take this simple algebra, x1 of xn quotiented by x1 of xn for L or some L greater than 2. Then also if you calculate, you come with a similar sort of groups, GLN for unipotent, and unipotent groups are rational, so this group is also rational and hence R. And this is also some simple algebra you can calculate, that you take the algebra to be x quotiented by x square y square. So these are all finite dimension, you can check. And if you calculate, okay, this comes to your example that this is not going to be a connected group. So it has a finite part. So then if you take the connected component, you just remove this, and this is also rational. So these are all positive examples that showing you, okay, the group maybe you think of finite dimensional associative algebra going to be rational or are trivial locals. Okay, so that's why this come to our theorem. So what we able to prove. Okay, so we have only one condition put and over a perfect field. So you take your algebra over K, which is a perfect field, and then you always have it such decomposition using something called Wedderburn-Maltsev decomposition of algebras, associative algebras, finite dimension. You have a semi-simple part and a Jacobson radical, which is just a, so this is a vector sum, not a sum of algebras. This is a vector sum. The product is different, but you have a vector sum of semi-simple part and a Jacobson part. What do you mean by semi-simple part? So this is AS direct sum J, your algebra A, such that A quotiented by J also. AS is your isomorphic to matrix division algebras. You can always have this, but what condition we are putting that this is just a split finite dimensional unitless associative. That means your D's are just K's. Only condition we are putting here that your D's are just K, only the field K. Then you can actually reduce your problem to a smaller group. So we denote this group by GAS, which is you take all automorphism GA such that it fixed all elements of AS. Then we are able to prove that GA is R-trivial if and only if this group is R-trivial. So sort of reducing the first problem to a smaller subgroup, that G is R-trivial if and only if this group is R-trivial. And then if you put this condition, J square equal to 0, dimension of J mod J square is less than equal to 5, and rank of the group GAS, this group, is equal to the dimension of J mod J square, then this group is R-trivial. And J is the Jacobson radical, that means it is the intersection of left or right maximal ideals. So this gives you some sufficient condition under which this group is going to be R-trivial. So these are the positive result, and let's look at now apply this theorem to this case. Okay, so this case your J is 0, that's why this group is R-trivial. This case, if you calculate the rank of the group, it is coming to the, and if you have, so you can calculate the Jacobson radical here and calculate the dimension of J mod J square, then it will coming to the rank of the group. You can calculate that. So that's the positive result. Then here also you calculate, it is a very easy exercise. You can calculate the Jacobson radical of this algebra, and you can see that this dimension J mod J square is equal to exactly the rank of the group. Again, the result follows. And here, if you calculate the dimension of J mod J square, it is actually 2, which is less than 5. That's why this group is rational. So these are all positive results, which actually showing that okay, our theorem is true. But see, the thing I now want to mention that okay, we make the thing much more bigger because we have no condition, no sigma, nothing. We have the finite dimensional algebra. The group is much more big. So maybe you think okay, you can always have a connection between 2 points, map between 2 points, but that is not true. So then it comes to our next theorem. So then it comes to our next theorem that bound dimension J mod J square is 5. it is strict. After that, you always can construct a algebra whose automorphism group is not attributed. So for each n, there exists a finite dimensional commutative associative algebra an over a field an with dimension of j mod j square is greater than or equal to 2n, where j is the radical of the n such that the GAN is not attributable as a k. And you can also calculate, so you exactly calculate the groups or the rank of this group, that is n plus 1. So it's showing that okay, n greater than if you put n equal to 3, that means it's 6. So if your dimension j mod j square is more than 6, you can always construct an algebra. I'm not saying all algebras are going to be give you a non-attributable group, but for you can always have an algebra whose automorphism group is not attributable. For dimension j mod j square. And for each cases you will get, and also each cases you have to change the field. So this is the recursive construction that for each n you are doing this, but the construction is remains same, some sort of similar. So this is the result showing that okay, these groups are not going to be always attributable. So there are plenty of examples, plenty of algebras where your automorphism groups are not attributable. So no need to bother about rationality. So this is you want to talk about. Yeah, 4 minutes. Okay. So this is this, and okay, these are the references we have, and this is the paper just December archive about this talk. Thank you. Yeah.
I was looking at questions of random generation of associative algebras a little while ago, and that like the result was something like if the generation function is maximal, if there is a condition on the Jacob's theoretical phase, the condition we have quite a lot of your condition.
Yeah.
So I'm sort of wondering, one can say if there's any connection between the rationality of the order proof just simply because the condition.
Yeah. Actually, the thing we noticed here, the main problem which is creating in this rationality or attributability problem is the Jacob's radical. That is the main thing. We need to tackle that thing very nicely. And I think there is a result by the representation by Quiver. If you have a split algebra, finite dimensional associative algebra, then by Quiver, so this gamma is a Quiver, which is a graph, finite graph. You can represent your algebra with this, which I has some nice property, which is called admissible idea. Then now we are actually trying to, in spite of Jacobson radical, we are trying to look at this idea to study this problem. And this is the main thing to use. And I think also what you're saying that, okay, there is a relation, maybe there could be a relation with rational problem. Because this is the important part of ZD.
What I was just wondering, what's the specific? Is there a specific? Is there a significance to j by j squared being at most 5 implying? And so you've got example for 6 and above.
Yeah.
What happens for when j by j squared is 5 and below?
Okay, so these are the very so if you you can bound your group rank by the dimension j mod j squared. When it is less than 5, you can sort of decompose your torus, and we use that decomposing of torus in such cases to study the rationality properties.